Welcome everybody to physics here. We're going to be talking about mirrors. And the first thing I want to tell you about is this formula. And we say to remember, if I do, I die. So you can think of smoking or other hazardous events. If I do, I die. And just so you know what this is, this F is going to be the number for the focal length from the mirror measuring on the principal axis. This is the distance of the object from the mirror, distance of the image from the mirror, all from the principal object, or from the principal axis. If we have a mirror situation like this, and we have a focal point here, we know that this mirror here is going to converge all the light rays that bounce off of it, and they will converge at this point called the focal. And the reason why they are converging is these rays are coming in and they're following the principal law of reflection, which if you have a tangent to the curvature of the mirror and you get the perpendicular there, that's called the normal. And this angle is supposed to be, or is, by the principal law of reflection, the same as that angle. So that's what governs this idea. But we can see that here at this focus, this type of mirror, which is called a converging mirror or a concave mirror, has a real focus. And so when we're talking convention of any of these numbers, if it's real, it will be a positive number. So in this case, the focus would be a positive number. Now, if we had an object here, and we're talking about a converging lens, and all converging lenses, by the way, have real foci. If we have an object, which is typically drawn as an arrow, and we're trying to figure out where the image is going to be, if we use ray tracing, there's three rays that we're always going to be using. We only need to use two, but there's three possibilities. But before we talk about that, since light is spherical in nature, you'll get rays coming off in all directions. And that's why you can see, you can see this image over here, you can see it here, over here, over here. But we can't talk about all those rays, so we have to come up with a system to show where the object would be. So here's the system. Like I said, there's only two rays. I'll tell you all three of the ones that are possible to draw. The first one comes in parallel to the principal axis. This line here is the principal axis, and this comes into the mirror parallel. And then the law of reflection that we talked about ends up shooting this one through the focal. Now, if my geometry was just perfect, you would notice that these would be the exact same angles. But the kind of cheat is to shoot it through the focal, because we know that's what actually happens if the geometry is correct. Okay. And then the other ray then is one that goes through the focus first and then goes parallel to the principal axis. So it's kind of the opposite of those two. And see right here is where these rays converge. That would be where the spot that I started with, that would be where that spot is. So if I draw in the image, it would be like this. And the image always goes down to the principal axis, because we can see if we had a ray here in the principal axis and it bounced in, the tangent would be right on the normal, so it would bounce right back out. And so it's pretty easy to tell that the tail is going to be down there using that idea. Now, it just so happens I must have been right on the center of curvature here, or the radius, they call this. And they're saying a radius as if this was a, entire circle here of a lens, or of a mirror. Okay, so when we're talking about sign convention for the object, for our purposes, the object is always real. And if it's real, then it's a positive number. So this case would be real. The distance would be a real, or would be a positive number. Now the image here can be fake or real. The one thing you have to remember is if the image is inverted, and you've done your ray tracing correctly, then it's real. So inverted image is real, and therefore the image number here would be positive in this case as well. Okay? So I'm going to show you a couple other instances where we can have ray tracings that are a little different than this. Okay. Incidentally, real equals positive, fake equals a negative number in this sign convention. Okay. And this sign convention is for if I do, I die. The one I'm telling you. Real is positive, fake is negative. If I have a mirror, a converging mirror, focal here, let me ask you, is this focal real or fake for this converging mirror? Yeah, it's a real focus because it's actually, it's a real focus. Energy truly is focusing at that point. So in this case, the F here would be a positive number again. Okay. Now if I put my object right here and do a ray tracing with this one's a little bit harder. We can still come in parallel to the principal axis and then shoot through the focal. I should label this as focal first. But then the other one that we would use is going to go this way. Now, you can't tell, but I have a ruler lined up with this as if it's going through the focal, and then I start drawing my actual ray at this point, and then it bounces parallel to the principal axis. Okay? So this is a little different because in no way are these rays going to intersect each other. They're going off into the distance. There's no real intersection, so I know right away I'm not going to have a real image. So in this case, what I have to do is called back tracing. And the back tracing is always of the reflected rays. So this is my reflected ray. So I'm going to back trace along that line behind the mirror. And this here is my reflected ray for this. And I'm going to back trace along that line for that mirror. And I'll find at this point is the intersection. And right there then is my image. Okay, so the question is sign convention for this, and the distance of the object for this, is this going to be a positive or a negative number? Is the object real or not? Well, for our purposes, the object is always real, so this will always be a positive number. How about the image? Is this a real image here? This is not a real image because it is not inverted. So real image is always inverted. This one is not. And also you can tell if you have to do the back tracing, there's no real convergence of the energy, so there's no real image. You cannot see this on a screen. You cannot project a fake image on a screen. That's why in the lab that we did on that last convex lens or convex mirror we used, we only saw light. We never saw an image on the screen. So this time, this number is a negative number because it's it's a negative, it's a fake image, so the distance number is fake. Okay. Now that we're on this, I want to show you the other formula that's on that worksheet. And that other formula is this. Magnification equals high hole equals negative dido. So this is really three relationships. Here's one formula. Okay. Here's another formula. And then the last formula is this. So we can see there's actually three formulas there. Do you see that? Now I want to tell you, the reason why I brought this up for your attention here is because high hole and magnification don't follow that fake is negative, real is positive convention. What you find with magnification and high hole is, and you'll see this in the math, if these are on the same side of the principal axis, then both of their numbers are going to be, well, in this case, positive, but they both could be negative too. So only when you have, like if your high is a negative number and your hole is a positive number, that means that they're on the opposite sides of the principal axis, like our last picture. So if I had, an object here and I ended up having an image here, then this would be a positive for the height of the image, and then this would be a negative. And it just means it's on the opposite sides of the principal axis. Okay. So I'm getting the feeling that we need a few more examples of ray tracing, because we have other lenses. And in this case, our lens here, if our focal is over here, but the lens a lot of times has these hash marks on there, or this is not a lens, I'm sorry, this is a mirror. Our image is over here, or our object is over here. How do you ray trace this? Well, kind of the same way. First you come in to the parallel to the principal axis, and then you can't see what I'm doing here, but I'm lining up my ruler with this. And then I can see where my reflected ray is going to go, right along that same line. And then the next line that I draw here, you can't really tell, but I'm actually lining it up with this. And the way I got that section is because I had my ruler going through that focal. And so I come in, and then I bounce parallel to the principal ray, or to the principal axis. And those are my two rays. So now I have to back trace, because I have, again, no convergence of these rays, so I'm not going to have a real image. It's going to be fake. So you always have to, again, back trace the reflected rays. So this is the reflected ray. So this one is back traced right through the focal. And then this here is the reflected ray here. So this one is going to be back traced here. And then at this point is where I will have my image. Okay? So if I was going to use the if I do, I die formula, the focal here, is this a real or a fake focal? It's a fake focal because you can see there's no concentration of energy. The rays are actually bouncing and scattering. So there's no focus or concentration of the energy. So this number here is going to be 1 over a negative number here. Do you understand that convention? And then the distance of the object, well, the object is always going to be a positive number. And the distance of the image here, though, is going to be a negative number because this image is upright. And real images that can be shown on a screen